Good day, everybody. I would like to start off by saying thank you for joining us on this technical topic webinar today. Can everybody please disable their notifications by simply going to my settings, the cog symbol in the bottom right-hand corner of the screen, as illustrated on the screen. Secondly, go to notification settings and untick all the boxes as depicted on the screen. Thank you, everybody. So can everybody kindly do that, please? The technical topic webinar today is CFD simulation of shock patterns downstream of a rocket nozzle, which will be hosted by Mr. VJ. These are the common questions usually asked. Okay. Within the next 2 business days, an email with the link to the video recording and a copy of the PDF slides will be sent out to each participant who registered for the webinar. Please keep an eye on your spam folder. For attendancy of technical topic webinar who are present in person, we offer a complimentary digital certificate of attendancy. At the conclusion of this session, a link and a QR code will be supplied that will take you to a brief form of a survey that you must fill in order to obtain one. When everything is finished, we'll try to mail your certificate to you within the next 4 business days. If you are new to our webinar, here is some information about EIT. We are among the fewer engineering specific institutions in the entire globe. Currently, we provide a variety of industry-focused courses, mostly in the fields of civil, mechanical, electrical, and industrial automation engineering. These courses vary from short courses to Doctor of Engineering degrees. Since all of our courses are provided online, in some cases also on campus, students may study from anywhere in the world, also have the option to study engineering in Australia if they so want to. The Australian government recognizes and accredits all of our vocational programs and higher education degrees. But we also offer a number of courses that are specifically recognized under the one of the 3 international accords: Sydney, Dublin, and Washington. And I will pass the whole presentation to Mr. VJ and he will take you guys on this journey today. Thank you.
Thank you so much for the introduction, Molifi, and welcome everyone to this session. My name is Vijay Kumar Veera and I'm your presenter. I'm an aerospace engineer with about 11 years of experience in using CFD methodologies to simulate both industrial and academic problems. I have BTech bachelor's and master's degrees in aerospace engineering from Indian Institute of Technology in India, and then MPhil degree in engineering from Cambridge University in the UK. And I have worked with quite a few organizations, both in Australia and United Kingdom. Some of the names you might know are Red Bull Formula One team, Mercedes Formula One team, Boeing, Airbus, Thales, and in Australia, Defense Science and Technology Organization, Fisher and Paykel, who do some of the home appliances. These are some of the notable clients I've worked with. In my current role as unit lecturer and course coordinator at EIT, I have helped develop lecture materials for teaching advanced fluid dynamics and the introduction to aerodynamics units. And there, the focus is on teaching you theory and also showing you how you can verify that theory through numerical simulations, and that is similar to the the way I would like to structure this webinar. And you're welcome to check out these units if you're interested in the content I'm presenting in this next 1 hour. So with that, let me go to the agenda. So I'll start off. We've gone through the welcome and introduction, and next is I'll talk about how CFD as a tool is useful in understanding the flow patterns within supersonic flows. Then we look at CFD simulation methodology. So what are the key steps in conducting a successful and reliable CFD simulation? Then I will change track and share my screen and show how to create I mean, I've done the geometry, but how to create a mesh on a given geometry, how to set up the case in the Fluent software, and what solver settings are necessary for simulating shocks um, within a supersonic nozzle, and then how to post process the simulation, and then we'll look at conclusions on any questions you might have. So feel free to stop me at any time. I'll be happy to explain things over. So this is my second webinar with EIT. I'm not sure if some of the audience have attended my previous one. In my previous one, I showed how we could use CFD techniques to understand what's happening in the intake of an engine, so of a engine of a supersonic aircraft. So this time I'm switching focus to showing you what happens in the back end or the exit of the engine. So there you have a nozzle, and so usually more I mean frequently you will see these kind of flow patterns that I've highlighted in this blue box, where you see some kind of alternating structure between hot luminant gas and then cold non-luminant gas. So these are like a series of disks or rings, and they generally occur when the pressure at the of the flow or air leaving the nozzle is higher than the surrounding pressure. So it creates these patterns, which are colloquially called as shock diamonds. And in this webinar, we'll see how we can use computational fluid dynamic techniques to virtually simulate these shock diamonds that are observed in these supersonic exhaust plumes. And I'll be using Ansys Fluent, which is a very widely available commercial CFD solver. Okay, so before we try to simulate it, let's just understand a few of the flow physics in what is called as a shock diamond. So let's look at this picture on the right. Um, if we look at so there's a source which is named as a high pressure reservoir. That's basically the hot air coming out from the nozzle. So this is a compressed version of the nozzle, but you see there's a converging section, and then there's a diverging section, and in between there's a there's what is called as a throat. So throat, this one which I'm highlighting in red, that's the smallest cross section area of the nozzle. And in order to achieve supersonic flow, you need to have sonic flow, or the speed of the air should be equal to the speed of sound at this throat section, which I've highlighted in red. So now once if you have this kind of an arrangement with converging diverging sections and the Mach number equal to 1 at the throat, you will see that at the exit the flow becomes supersonic. So let me change the color to be so the flow at this exit plane is supersonic. And when the flow is supersonic, um, what would happen is the there's also a pressure associated with the supersonic flow, and in case the flow is the pressure of this exit flow is greater than the ambient pressure, then what would happen is the flow will expand, and if it is slightly lower than the ambient pressure, then it will create these shock waves. So depending on what the criteria is, the pressure is, you'll either get a shock wave or an expansion fan. So what shock waves do is they decelerate the flow, and when they decelerate the flow, they lead to an increase in the pressure. And when if the pressure is, and that happens when the exit pressure is lower than the ambient. But if the exit pressure is higher than the ambient, then there'll be an expansion where there's more pressure. It'll expand into the flow will expand into ambient and create like this kind of a diverging pattern. That's called the expansion fan. So you see this, it's the flow will expand until it until the pressure equalizes across this point, and across this point the pressure will equalize, and that's like the boundary of the jet. And then when when the flow accelerates here, expands, when you get to about this point, you'll see that the pressure here at this location is lower than the ambient again. So it becomes, so if I just draw it, P is less than PA, which is P ambient. And what that does is, because there's a pressure deficit, then there'll be these compression fans. So there'll be, the flow will undergo compression because the surrounding air has more pressure, so it's trying to squeeze it. That's why you see this bubble going down. So here the bubble is, or the volume is expanding because the pressure is higher, and then there's an equalization, and then the pressure starts to as the fluid pressure, the flow pressure, jet pressure reduces, then the surrounding flow will kind of try to squeeze it in, and then that causes another shock wave to be formed, this red one. And then again the process repeats. So there's a shock wave, and that creates an expansion fan. So that kind of so all this that I've explained, so if I highlight this, so all this that I explained happens in, if I go back to the previous slide, it happens in one of these cells that I will highlight in magenta. So if I just highlight the, so each cell that I've highlighted with this magenta dot, that's all this flow physics is happening in that cell. And then this pattern repeats when successive cells get created, and in each cell, because of these shocks and other losses, the pressure keeps reducing, which means the strength of the shocks and also the strength of the expansion in each cell progressively reduces, and finally to until it gets to a point where the pressure is equal to the ambient pressure. Okay, so that's the flow physics in the shock diamond, and it's very interesting. And as you can see, it shows, it creates some amazing visuals. And if you have seen movies like the recently released Top Gun, you might have maybe, if you get a chance to watch it again, just see if you can pick these out. But because these are very common at the exits of exhausts of supersonic fighter jets. Okay, so that's basically the physics that we want to simulate. And then I will quickly go into the methodology, how we are going to solve this problem using CFD. So the thing is, every CFD problem broadly has the same methodology. The methodology is identify the fluid domain to capture the necessary physics. So in this case, I'll show you how we have a fluid domain to capture the shock patterns. Then we generate a mesh that captures the regions of high gradients with sufficient resolution. So wherever we have flow acceleration or deceleration happening at a high rate, we need to have a very small mesh and a fine mesh to capture the gradients. Then we need to choose the appropriate models to represent the flow physics. So in this case, this is supersonic flow. So in supersonic flow, we need to ensure that the density is related to the pressure and temperature using the ideal gas equation. If we just assume constant density, our results will be incorrect. Sometimes the solver might not even converge. Okay, then also specify the correct boundary conditions. Mulefi, can you hear me? I think a couple of students or attendees are saying that they have problems with audio.
Yes, I can hear you perfectly.
Okay. Yeah, okay. Maybe those who are having some issues, maybe it's something to do with your internet connection. I hope others can hear me okay. Uh, or otherwise, we are anyway recording this and you can watch it again at your convenience. So as I was saying, we need to next specify the correct boundary conditions. So in this case, the okay, thanks, Mohammed and Ujwal for the feedback. Thank you so much. Happy to hear that you're able to hear and there are no issues with the audio. So we specify the correct boundary conditions, and in this case, it's the upstream pressure and the exit pressure that we need. Then we choose the right solver settings to run the solver. So again, if you go into the intricacies, the you have different solver settings which are optimum for high speed flow and low speed flow. So we'll not go into a lot of depth in that in this webinar, but if you take up the units, especially the introduction to aerodynamics or introduction to advanced fluid dynamics, these kinds of will go into a lot more depth in on how to simulate subsonic and supersonic flows. Then we solve the governing equations, which are the Navier-Stokes equations, iteratively until the flow field satisfies the governing equations. And then finally, we can visualize the flow field by plotting contours, vectors, streamlines, and animations. If we have any available experimental data, we can compare with it and to evaluate how efficient our CFD model is. And depending on this, what we learn from this process, we can go back and repeat this process if necessary. Okay, so we can go back and make modifications or refine the mesh, go back, run the solver, and validate the problem again, the results again. Okay, so that's the broad methodology. Then now let's go into how to create the mesh on a geometry that we have done. So what I will do now is I'll share my screen, and then so I have Spaceclaim, which is a geometry generation or cleanup software that is available. So this region is the exit of the nozzle. So this region is the nozzle. So this is the subsonic section, which is the converging section. There is this region, which is the throat, and then this line is the diverging section. Then there is this region, which is the ambient. So this is an axisymmetric problem, which is like a slice of what's happening in the in re, it's imagine you take a slice through the nozzle, because and about the axis of the nozzle, the flow field is largely the same. So in order to um, get a more efficient or have a more efficient solution, we just take the slice and then simulate the um, flow on that slice. And what that will allow us to do is it will allow us to capture the gradients in more detail. So this is a common and industry accepted practice where you just do a 2D simulation, two-dimensional simulation to capture some relevant flow physics. Okay, so now that I have this geometry, then the next step is to create a mesh on it. So in Spaceclaim, there's a meshing ribbon which you can access through Spaceclaim options. And in Spaceclaim options, there is a, if you go to customize, so customize and then ribbon tabs, there's this tick box for mesh, which is not switched on by default, but if you switch that on, you will get this mesh section. Click on or off. Right now it's switched on. If it's off, everything will be gray like this. So click the on button and choose the physics type, which is the fluid dynamics. And the way this meshing works is it tries to create a structured mesh. So like a nice good looking structured mesh on this geometry. So I'll show you how to do that. So you just use this bounding box option and click on the green tick. So what that does is it tries to break up the geometry into blocks, which you can assign like divisions and then get a structured mesh. And then, so if you see this mesh is not really good. So you see that this cross section, this convergent section is not respected, and it doesn't look like the geometry is being, it's respected here, but it's not being respected at the important regions, which is the exit. So the way to do that, fix that, is to use the tools available to split the problem or the domain. So I made a split here, and I'll also make a split here. So what that will do is, I will this small so if I so this patch that you can see, I will map the whole nozzle to this patch, and then I'll map the outside ambient fluid to these two patches. I actually don't need this patch, so I use the delete option to get rid of the patch. And then if you see, it has definitely improved a bit. Now what I will do is, I'll split this region again. So this, I'll split it again, so that I'll have two sections, where this section I can map to the converging section, and this section I can map to the diverging section. Okay, I'll show you how I can do that. So there's an option to associate, where you can link the geometry of this block or a mesh to the underlying geometry. And then if I click OK, you'll see that it is snapping to the geometry that we have. So click OK, and you see it is kind of snapped, but it's still not perfect, and we'll see how to improve that. So I'll snap this to this. Sometimes it's a bit tedious, but it's worth the effort. Okay, so I'll snap this to this, and then snap it to this. Okay, so now we are getting somewhere. Now next thing I need to do is, I need to give more cells here. So you see there are only 3 cells to capture this whole region. We need a lot more than that. So I'll use the size option to select, and then specify instead of 3, so I'll use 50. And then what I will say is, I want clustering um, about the center, which is where the flow will become sonic. Okay, so that's with number of 50 divisions. You see now it's respecting this a lot better. So I'll select this, and again uh, this lock indicates hard behavior, which means that constraint will be respected no matter what. So here what I will do is, I'll go, because it's longer, I will use 100, and then I will use this case where I have a fine mesh over here, and also a fine mesh at this exit. Okay, so that's and then maybe what I will do is, I'll increase the factor to be about 10, and then have it like this. If I just have it as 10, and then click on the green tick, so what that will do is, it will make sure that the mesh here is the same. So we don't want sudden jumps in the mesh for us to get a good quality answer. So next step is for these. So again I will have, say, 200, but this time I just want a fine mesh here. I don't really want a fine mesh here. So I will use 50 and copy to parallel edges. Um, okay, so if you see here, so 20 is a bit too low. Make this 50 like I thought initially. Yeah, so that is a bit on the lower side. Let's just go to 100. I think this is a bit better. So that's 100. And what we will do is, we'll also refine this mesh, this region. So I will use again 50 cells here, and I want to have more mesh along the walls. So make this about 10. Um, I want it the other way. So if I click, make this 50 as well. That will allow us to get a very fine mesh over here. So you see this dark region indicates there's a fine mesh there, and wherever it's dark, it indicates mesh refinement. So now my final section is to refine this region. Again, I will put 100 divisions and then give it a bias of say 50. I think I need a lot more than 50, maybe 500. So maybe I need a bit more. Maybe 1,000 would be better. Okay. So let me, I think, make it 2,000. No, two. Yeah, sometimes you'll have to just modify these until you get to the required value. Yeah, that's a bit more like it. So okay, so that's our mesh, and yeah, I'm happy with this mesh. um, the other thing to remember to do is just make sure you save this. So I've just saved this problem, and I also need to tell the software what is my inlet, what is my exit. So for that, what I will do is I'll hide the underlying geometry and then go to groups, select this inlet, and then click on create named selection and call this inlet. um, okay, let's okay, so that's my inlet, and then this is my outlet. So just OUT. This is my far field, and then this is my um, ambient. So there'll be some air coming in. So that's my ambient, and then this would be my axis. So this would be my axis. So I'll just call it AX. So I have my pressure inlet, outlet, far field, ambient, and then axis, and then this is my nozzle wall. Control G. So that's my wall, and what I will do is I will, so there's an option to switch off the mesh and then do the association. I've done the association throughout. Okay, so let's save this and let's try to generate the mesh or set up the problem. So if you go to this workbench tab and there's an option to um, send this to the solver. So click on that mesh to solver, and what that will do is it will launch Fluent in the background. So and then I will just try to hit select, and then that should allow me to run. Okay, so sometimes it will give you an error saying number of users are exceeded. So let's just go back, and I can open it from the start menu, and it should have the path remembered. So this is the one I just saved. So let me just start with the selected options. So let me see if there are any questions. Okay, I don't think there are any questions so far. So right now, this is the console where it's reading in the faces and it's reading the mesh. So I have my wall, nozzle, ambient, far field, all those have come through. And if I want, click on this boundary condition, and then so I need to just specify what these are. Right now, it thinks everything is a wall. So if I click display, so there's like this white region. So this will be a pressure inlet. So with gauge pressure of 1 atmosphere, or maybe it's in high altitude, so make it 0.1 atmosphere. Go to units and then go to pressure and set this to be 1 atmosphere and units of atmosphere. So make this 0.1 atmosphere, so which is 1/10. Click apply. Then I have my far field, which I can just call it to be a wall, but assume that there is no resistance. So it's like there's a option to just specify there's no shear at that location. Then outlet is a pressure outlet, so just do pressure outlet. And then this also has the same ambient pressure of 0.1 atmosphere. And then I have my, so the far field is done. Surface, so this wall surface is actually the bit between the fluid, the two sections of the fluid. So what that will be is that should be an interior. Interior is internal, so that flow doesn't, there's no obstruction to the flow. So the ambient is done. So I have my, so let's draw this. Okay, that's our mesh, you can see. So if I want, I can choose, I can look at, so so if I hide this interior and then look at this wall 14, it should be okay. So for some reason the axis is connected. Okay, fine. We can quickly do that. So sometimes I have to deal with such kind of issues. So I'll just separate this with, click separate. So if I go to display again, so that's my axis, this wall 14. I'll just edit that, call that an axis. Apply, and then change this to be an axis. And now I have my, so that's my wall nozzle. This wall surface is an interior, that's fine. This wall, that's my inlet. So if I connect these two, that's my inlet. So wall 003, 14003 is my wall, is my inlet. So I'll just name this a pressure inlet and then rename it to um, in yeah, inlet. And then I'll assume that the ambient pressure is 5 and then or 10 atmosphere, and then supersonic or initial gauge pressure is say 3 atmosphere or 5 atmosphere. What that means is at the exit you're getting like about 5 atmosphere. So now that I've done that, I need to specify the material properties. So we need to specify that air is a, right now the default is air is a constant density. We need to change this to ideal gas, and there are options to get a better um, capture of the properties. So these are the information that you These are the information that you need to provide to explain to the solver how the material behaves. So for this thermal conductivity, I'll use kinetic theory. For viscosity, I'll use Sutherland's law. I'll just use the defaults, or I can use kinetic. Um, I think I'll use kinetic theory, and then other things I'll leave as constant, or as the default values. And then we need to check what model we are using to capture turbulence. The industry standard is to use SST K omega model, but I'll switch on viscous heating, curvature correction, and compressibility effects, because those will give you a better capture of what's happening at high speed flows, which is our case. So just say okay to that. Now, also this problem is axisymmetric, so I need to use the correct axisymmetric formulation, and I'll use the density based solver, which is um, good for high speed flows, supersonic flows. Okay, so these warnings were when I changed the when I created this axis, it gave us these warnings saying change to axisymmetric problem, otherwise you'll get errors. So that's fine. Also do a mesh check to check everything is fine. Looks like everything is okay. Look at the quality. Quality, it should be more than zero point 0.1. I have the orthogonal quality as 0.8, which is also very good. Now I think I'm good to run this. Before I do that, I need to track some information. So for example, I can look at the force to, this is to evaluate the convergence of the mesh of the simulation, sorry. So in the force report, I can look at the force moment, and if I look at the um, so x-axis is along the horizontal and y-axis is along the vertical. So when the flow is accelerating, there'll be a reaction force on the walls of the nozzle in the negative x direction. So so call this and that will be the thrust produced. So call this thrust. Um, so nozzle thrust, and then select the wall nozzle, and then it will be about either plus x or minus x. So let's put around about the minus x axis, and there's an option to write it out as a file. Okay, so there's also an option to uh, create like an area weighted average of say Mach number. So go to area weighted average of velocity, and inside velocity you'll have Mach number, and that will be at the wall surface. So if I draw the wall surface, um, so that's exactly the exit of it's at the exit of the nozzle, if you saw. So at that exit, I want to look at what is the area weighted average Mach number. So if that becomes flat, that gives me additional confirmation that it is the simulation is converged. So area weighted exit Mach number. So I can name it like that so that I know what I'm plotting next time. Similarly, I can look at area weighted temperature, pressure, and all that at that exit. But for now, we can use these two. Another key thing to remember is usually this the flow in at the exit of the nozzles is very hot. So I'll have to specify it's not 300 Kelvin, it's close to 2500 Kelvin. So I'll click apply, and then close, and I think I have everything set. I'll just write the case file. So cd nozzle.case.h5, and then it's finished writing in less than a second. And now I will right click to initialize, and what that will do is it will create like a random, not a random, initial starting point for the solution. So let's look at for example contours of pressure. So this is a static pressure contours in atmosphere. So there's 5 atmosphere here, and then there's close to 0.1 atmosphere here. That brings me to another point where usually the operating conditions assume the ambient operating pressure is 1 atmosphere. I'll make that 0 and reinitialize. Yeah. and then I can call this contour pressure, click save display and switch on fill. That is my pressure contour. There's an option to change this in color map options, the coloring, to use what is called as say field pressure. So that gives us a slightly different color scheme. Okay, so here the idea is red and blue indicates regions of high pressure and low pressure, and the one close to white indicates like a midway between the two. So that's my pressure contour. So I'll just look at velocity and then Mach number contour, and then call this contour Mach number. And again, I'll choose the color map to be field velocity and then click save display. So that's my velocity field. So it's showing a Mach number of 0.5. There's another option to have the color map to be top so that it is not using up all your apply, close, save display. Then I'll just do one more for temperature. So go to temperature, static temperature, call this temperature, and then go to color map options and then field temperature and make this go to the top, apply. So that's my temperature. Right now, everything is at a low value. So save this again. So this time I can write out the data file where I just overwrite the previous one. Now this is a reasonable starting point, but for high speed flow, there's a way to improve our result. So you have to go to the search bar here and type FMG, and what that will do is that will solve uh, the Euler equations in this domain, and you will see how this flow field will change when it solves the. Okay, fine. I think it gave me an error here. So looks like it doesn't like one of our boundary conditions. So maybe I'll make this 2, apply. So I'll just initialize this again. So sometimes, okay, yeah, I'll just initialize with hybrid and then use the FMG initialization and see if the flow. Okay, so there's sometimes you get these kinds of errors, and that's where we have to diagnose what went wrong. So looks like the pressure is too high somewhere. So let's go to ambient pressure. So that's total 0.1. Thermal is 300, that's fine. And then the outlet is gauge pressure is zero point 0.1 and 300 is the thermal. So let's just look at initializing. Okay. Let me just run it with these settings and see what happens. Okay, these residuals are behaving reasonably well. So this is the thrust generated by the nozzle. So it's about 12 kilonewtons. And then if you look at the exit Mach number, it's going up, whereas here it's tending to. So there's a big oscillation, but looks like the oscillation is coming down. Even these residuals are dropping. So the residuals dropping indicates that there's a there's the flow is getting to a point where the governing equations are solved. So when you are at the high values of residuals, the governing equations are not respected by the flow field, whereas here they are getting closer. And if you see here, the nozzle thrust has effectively flatlined and we'll see that the exit Mach number will also flatline. Okay. So I have a very fine mesh, that's why it's taking a little while. But you see that the thrust is more or less flatline, whereas this exit Mach number is still evolving. So we just need to have a bit of patience and just wait for this to converge. So let's look at the residuals. So usually this is what we do when we are running the CFD simulations. We just keep an eye on residuals or the other quantities of interest. So if you see the thrust, it has settled somewhere at about 9,500 newtons. So just below the 10,000 kilonewton value. And then if you look at the area weighted exit Mach number, again you can see that it's beginning to flatline. That's at about just over 3.5, Mach number of 3.5. So see that most of the residuals have become flat. Um, so continuity is a measure of the difference between whatever flow is coming into the system and whatever is flow is going out. So if it's a small value, it means that the flow in is close to the flow going out. Then we have the momentum equations x, y. So that is keeping track of how much momentum is entering the system and what is the momentum of flow leaving the system. Then we have the energy equation, which balances out the energy equation, and k and omega are the turbulent quantities. So we need to account for turbulence in high speed flow. So if you see this, so you can see that it's almost flat now. So let me run it for another till all the 500 iterations are done, and then we can look at how the results have changed. So it is slowly coming down. Uh, we just need to have a bit more patience and then run this for a bit longer. But for intents and purposes of this demonstration, we can assume that the solution is converged. So I'll write the case and data file with a preferably another name. So call this T, no, sorry, conv for converged, and say OK. And then let's look at how the Mach number has how the Mach number. So okay, let's look at how the static pressure has changed. If I click display for the static pressure, and then let's also make this take this to the top, apply. So we don't see a big change in the static pressure contour plot, but let's look at the Mach number contour. Can you see that? So there is low value here, which is close to 0. So that's, but then as the flow goes through, you see that there's this shock, there's this acceleration of flow where it gets to about Mach 5, and then there is a deceleration region, whereas it's less than it's about Mach 2, and then again it goes up and it goes down. So you see those cells being formed. And let's look at the temperature as well. So the temperature also, we see high values here, but then we see slightly lower values here, and that's because of some low velocity regions. And then you can see like a slightly higher value here. So the closer this is to white, the higher the temperature is. Okay, you can right click here and then it will show us the values. So if I go to the default, will get the value. Yeah, so it'll give us the value. So the probe position and the contour value is around 1100. So if we go back to temperature and then click here, you'll see that the value is about 500. So it is from here to here, it has gone up by value about 600 Kelvin, which is effectively double. Okay, so that's our temperature. Let's just do density as well. So density, and then go to make this top, and then call this field. Let's just use field velocity. So that's the density variation. Again, we see this dark blue, which indicates low density gas. Okay, um, call this contour density. So for all these, you can see that some of these are not really, they're not seen well. So even here for the Mach number contour, we see that it's a bit fuzzy. It's not well defined. So I'll just show you another way of tracking where the shock's happening, and that's in the derivatives and the strain rate derivatives. So if I click on compute uh, global range, sorry, compute, and then what I will do is I'll remove a couple of zeros from here and click save display, and again I'll take this color map to the top, and what I will do is I will use flame as the, so if you see here, now you can start seeing some patterns. So this region which I'm highlighting is the shock, and then there's this is a shear layer. So there's on top is the low speed flow, and then and in the middle there's the high speed flow, and there's a lot of gradient between these two streams. And again, this black region is again a region where you have high strain rate. So maybe let me just add a zero and display, no, maybe make this 1. Okay, so that's how you can uh, see the shock. Okay, so let's save this again. So, but I'll show you a nice trick to refine the shock capture further. What we can do in the software is you can automatically change the mesh where you have regions of high gradients. So, uh, go to aerodynamics, shock indicator, and density base. So, what this will do is this will look at where the density gradients are high and identify those as shock gradients, and then put more cells there. Okay, so if I click display, you it's these are the regions where the mesh will be refined. So you see these, so these are the regions where the mesh will be refined. So I'll say okay. Okay, fine, close. It already has. um, and then what I will do is I will run this for another 100 iterations and hit calculate. What will happen is it will run about 20 iterations as usual, but then when the 20 iterations complete, it should refine the mesh in the regions that it has highlighted here. So it's just yeah, it was just waiting for something to clear. And yeah, so it's starting to run the simulation again. So the residuals will continue from where they left off, but when it hits that 20 mark, you'll see that there's a big jump. And that big jump happened because if I show the mesh, you will see that wherever you have regions of high gradients, you see a mesh refinement like this. Okay, so there's a mesh refinement here, there'll be another mesh refinement here, and then click calculate. And what that will do is it will cause a jump in the residuals, but then they should start dropping. The nozzle thrust and this exit Mach number should not significantly change. So the nozzle thrust is not changed significantly, and this is not changed significantly. So let me, sometimes if it doesn't show up, if you just close that, it will show it again. So let me run this 100 and then see how the residuals look like. So you can see that the jumps are progressively getting smaller, which indicates that the shock is being resolved well. So the thrust is not changed. The exit Mach number plot, let's close it and open it again. Okay, so let's just close it, and then if we draw the mesh again, you'll see that it has refined these regions a bit more. And let's look at the Mach number contour now. You see that there's a bit more definition that has occurred in these regions. And then if you look at the strain rate also, you'll see that there's a bit more definition that has occurred. You can do this successively to get a very high definition contour for these kinds of problems. So I think with that, I'll save this case and data file and then stop sharing my screen and then go back to the slides. I think Molefi, if you can share your screen with the slides, or maybe what I will do is I'll just share the files. Essentially, whatever I've shown in the subsequent slides is what I've demoed in the tutorial or in the demo. So these are how I've done successive iterations. So that's why we see all these jumps for the mesh refinement. And this is the force where you see that it's effectively flat line. And then these are how the density contours look. In this case, I used a lower temperature inlet gas. So if I reduce the inlet temperature to be about 300 Kelvin, you'll see these kinds of flow patterns. And then these are the Mach number contours where you can see successive iterations have improved the resolution with which we capture these shock nozzles, these shock diamonds. Okay, so in this case, the temperature is only varying between 37 and 300. So wherever there is high acceleration of the flow, you will see very low temperatures. So that's why if you have 2500 as the temperature at the nozzle inlet, it'll go down to about 500. So that's like 20% drop. I mean, 1/5 drop in temperature. And these are the static pressure contours where you see these successive cells being formed. And then these are like the strain rate contours where we can see those shock patterns. And this is a total pressure contour plot. So total pressure is a measure of how useful uh, the flow is in doing work. So for example, if you want to rotate a turbine or to create energy, you need or to accelerate in a nozzle, you need a very high value of total pressure. So the flow in the nozzle initially has a very high total pressure, but as soon as it encounters the shock, the total pressure gets destroyed, and that indicates the capacity of the flow to do work has greatly diminished. So just to summarize, I've provided a brief introduction of how to conduct analysis of supersonic nozzle exhaust pattern through CFD. We've looked at an example of how to do that. We looked at how to generate a mesh, how to set up the problem in CFD, and troubleshoot a few issues that might arise, and then conduct a CFD simulation and look at the results. And the way you can use this information to improve design is when you post-process the results, you can identify regions where the flow is not expanding. So you can play or you can change the shape of the diverging section of the nozzle to see if you can achieve more thrust. So there's a theoretical procedure for that using method of characteristics. I'll not go into that a lot, but that is used a lot in coming up with the designs for nozzle rocket nozzles. So all these rockets that go into the that carry satellites into the atmosphere, they are developed using what is called as method of characteristics. So you can use that to further, and CFD to further refine your design. And the other key selling point for this simulation based methodology is that it's more cost effective than conducting experimental analysis. So you saw over 1 hour we could get an idea of how to solve this problem in on a computer and get answers which are close to experiment. If you want to do the same experiment, you would have to build a big tunnel and then run this for a or pressurize gas to very high atmosphere, which means you need adequate storage capacity, and you need really sophisticated um, uh, instrumentation to capture things like shocks and all that. So you can do the CFD analysis in the fraction of a second of cost of doing an experiment. So I think that's all I had to share. I think I can pass it over to Molefi.
Thank you very much, Mr. VJ. That was a very interesting presentation.
Thank you,
Um,
Molefi.
no problem at all. Um, our upcoming webinars, don't miss out on EIT's Virtual Open Day, which is happening on the 27th of October. You can register for the event on the link that I'll put in the chat box just now. If you want to register for the open day, you can register by the link I just sent in the chat box. There's a list of our upcoming courses, and we have a range of courses in civil, electrical, mechanical, and industrial automation engineering. To see our full course schedule, please kindly go to the link in the chat box, which I'll send just now also. To receive your digital certificate of attendance for participating in this webinar, please fill out the form and survey here or scan the QR code. I will put the link also still on the chat box, and you can also scan the QR code to go to the survey which you have to complete in order to get the certificate of attendance. I'll leave this slide for 5 minutes just for everybody to scan, for those that are going to scan, and to get all the information you need. Yes, the video will be shared with everybody. I can see the questions in the chat box. Yes, the video will be shared with everybody as long as the PDF slides also. So within the next 2 business days, an email with the link to the video recording and a copy of the PDF slides will be sent to each participant who registered for the webinar. Please keep an eye on your spam folders. So thank you very much, everybody. If you have any questions, please do ask now, and Mr. VJ will answer all your questions.
Yep.
Mr. VJ, I think you have a question in the chat box.
Yep. Yeah. So Upadhyay or Krishna, I guess, or so. I would recommend using Spaceclaim for for doing the geometries, because design modeler actually is, it's not being uh, developed a lot. So and also Uday, your question how to get the actual dimensions of the nozzle, um, maybe I can share the geometry file with Molefi, and while uh, would it be possible to uh, provide that geometry file, Molefi, with the recording?
Yes, it will, definitely.
Okay, so I'll just send the starting like file. Only thing is you need to have a copy of the Ansys student software, which is the latest version. Um, And
Okay.
yeah, so maybe I'll just provide a link to where you can download the student software. It says you
Even perfect.
student
There's
download.
another question for you, Mr. VJ. How do
Yeah,
I get the actual dimension of the nozzle if I want to do simulation by
yeah.
myself?
So I was answering that one, that question by Uday. So if we can provide the geometry file along with the link to the recorded webinar, then I think that will answer Uday's question. So also for those who want to download the software, this is a free student version. The link I've sent you. Only thing is, if you click on the link, it will tell you the requirements, the computer requirements like disk space and all that. You need this along with the file, Spaceclaim file, for getting started. So and also uh, Krisha Upadhyay, for in response to your question, in meshing can we use face and mesh sizing? Uh, you can use it, but that is generally for unstructured mesh. For structured mesh, we just give the number of divisions like I did in the webinar. So you say select an edge, say I want 100 divisions here, select another edge, say you want 200 divisions, and it will create like a 100 by 200 mesh. And Alhamvi Sala, your question to what is the criteria to say it's a good mesh? You have criteria like orthogonal quality. So imagine you have a square. Square has orthogonal quality of 1, but if you you hold the square by two diagonals and pull it in opposite directions so that it becomes a very long parallelogram, then that will have orthogonal quality close to 0. So you need to ensure that your mesh is more like a square than a long parallelogram. So you have orthogonal quality where you set it to be 1. So you can check the orthogonal quality and set it to be 1, or set your mesh setting so that you have as high a orthogonal quality as you can. Thank you so much, Krisha Upadhyay. I think it's Krishna Upadhyay, but it's nice to interact with you as well. Thanks so much for attending the webinar. And for everybody else who's who is on the chat, that really nice talking to or interacting with you guys. And for those who asked questions also, thank you so much for taking your time to attend this webinar.
Thank you, everybody. Thank you, Mr. VJ, for answering everybody's questions. If you still have more questions about anything regarding EIT, can you please send a mail to the email address that I'll be putting in the chat box? Thank you, everybody. Thank you very much. Mr. VJ, thank you very
Thank
much
you.
for
Thank you
this
for hosting this.
interesting event.
Yeah,
Thank you,
thank you so much for
everybody.
hosting this, Molefi. It's really nice um, to have this hosted as well.
Not a problem. Here's
Thank
our
you.
contacts. If you need to reach us in any way, the contacts are showed on the screen right now. And thank you very much, everybody, for attending this webinar.
Thank you
I'll
again.
leave this for 5 minutes, then we'll wrap it up.